This is my lab 5 video. For this lab, we're going to choose our own adventure, and I'm choosing the falling slinky. So let's do this. For the introduction, in the video, we saw a professor was dropping a slinky from rest, and the bottom of slinky stays stationary. And we're going to use the model in closed grip to prove the ideal motion of slinky being dropped from static equilibrium. And we are going to apply the physical principles we learned in the lecture to the model. Our main question is, will the bottom of the slinky stay stationary? And here are the formulas and physical principles I used. The first one is Newton's second law. And we are going to use Newton's second law to update our velocity, which is Vf equal to V initial plus F net divided by mass and times delta t. Also, we're going to calculate our weight, which is very easy, minus mg times the direction vector, which is in minus y direction. And our drag force, here I choose our constant as 2.6 as the convention. So let's take a look at our model in closed grip. I basically divided it to two time periods. The first time period, t smaller than 0.457, is when the bottom slinky stays stationary. And you can see that, as I mentioned before, I have a F drag force equal to ball times mg times j hat, which is y direction vector, because at this time Fd is equal to F drag is equal to weight and F net is equal to 0, and I update the ball's velocity and the ball's position. And here when time is in the period of 0.457 and 0.657, the bottom of the slinky start to drop. So I update this drag force function as here, and then you can see the F net force change, and I update the new ball velocity and the ball position function. And here's my result. As you can see, it's a very ideal model. It suddenly drops at t equal to 0.457. And then let's take a look at our visual analysis in Tracker. Let's go. Okay, so you can see the graph of the y position is a little bit deviated because of the human errors. But it has a similar trend as my prediction model, and you can see that, as in the video, the bottom of the slinky do stay stationary at the beginning. And here is our result. Here is my result comparison. Basically, they have the same trend, but the Tracker video has a little bit deviated data, but it proves that our model is correct. Here are the useful follow-ups. As I mentioned before, the general trend of two resulted graphs is similar, and the Tracker slinky video has deviated in data, but the main principle the most important thing in this physical analysis is that during the first period, the net force acting on the bottom of slinky is 0, because F drag is equal to F weight. But after a certain time period, the F drag force is smaller than the weight, so the whole bottom of the slinky start to drop. And that's it. Thank you for watching my video.